Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on series inverter and parallel inverter. So first here, what is the series inverter? Series inverter, in this, the commutating elements, so the commutating components, that means inductor and capacitors are connected in series with the load, that is R. So then that inverter is known as a series inverter. So here this is the inverter, this is load, inductor, what are the commutating elements? Inductor and capacitor, and this is the load, the RLC, and this is another thyristor. So now here the values of inductor and capacitor. So now here the values of inductor are selected. So here by selecting proper values of inductor and capacitor, R is less than square root of under root 4L by C. So now this is the case. So in this case, here the system can be underdamped system. So underdamped system, so the anode, if any DC excitation is given to the RLC circuit, the circuit is in sine wave. So here when it is 0, so output current is 0, means when it will be turned off, so anode current is less than the holding current, so then only SCR will be turned off. So that is the case when anode current becomes a 0, so then the results SCR will be turned off. That is the commutation main purpose. In the commutation means the process of turning off process, either anode current below the holding current or apply the reverse potential to the thyristor SCR, then only it will be turned off. When it in this case, so the output current is sine wave, means here when it comes to the 0 and the SCR will be turned off, the anode current itself becomes 0 in this inverter, the resulting SCR turn off automatically. Therefore this inverter is also known as a series inverter, that means self commutated inverter or load commutator inverter. So it will class A commutation. Now here, so it can be, this series inverter can be applicable for high frequency applications. So now here that frequency range is 100 kilohertz to 200 hertz to 100 kilohertz. So now here what are the applications of series inverters? So first, it is used in the induction heating, fluorescent lighting, and sonar transmitters and ultrasonic generators. So these are the 4 applications series inverter we will use in these 4 applications. So now here if you see the circuit diagram, so this is the circuit diagram of series inverter. First, here R, L and C are connected in series. Commutating components L, C and L are connected in series, and in series with the, this is the load. Here we can see the V0, and now here this is the output current. So in the series case, same current flows to the each element R, L, C, and this is the thyristor T1 and this is thyristor T2. This VSC means that is VDC. This is the circuit diagram of series inverter. So now here in this there are 3 modes. In the first mode here, so in the first mode what will happen, T1 thyristor, T1 SCR will conduct. So now here in this case T2 SCR will be turned off. This is plus and this is minus. So it is in reverse bias mode. So it is T2 is turned off. So now here this circuit is, it's look like a DC excitation. This is short circuit DC excitation given to the RLC. So now here its output current is always sine wave. Already we have seen in the series off-bridge inverter with RLC circuit. So now here off-bridge and full bridge inverter. So now here DC excitation we are giving. So the current flows in this. So here This is the output current. So the output current is whenever DC excitation is given to any RLC circuit. So that output current is always sine wave. That means alternating. That current is alternating sine wave. So the nature of load current, this I naught is the sine wave. There is a underdamped circuit of commutating components. Now here by selecting the proper values of inductor and capacitor, by selecting R is less than square root of under root 4L by so here in this way, if you select this one, so how it will, when it will be this is when the system will be underdamped, zeta is 0 to less than. So in this case, this damping factor is in between 0 and 1. The system is in underdamped system. So now here zeta equals to R by 2L. So that is, so now here your case, if you apply Laplace transform to this one, so now here S square, already we have seen in the class A commutation SA, that is R by L into S plus 1 by LC. So this is the case. So that is a characteristic equation for this RLC circuit for I naught. So now here zeta equals to R by 2L and omega equals to 1 by root LC. So this is the case. So now here by selecting proper values of, so now the zeta is in between 0 to 1 means here the R by 2L, this value is must be, so now here R value is less than under root square root of 4L by C. So in this case, the SCR, this system is in underdamped means here, underdamped case, the waveform, it looks like this. So just go through the class A commutation video. So in that, when it is comes to the 0, the SCR T1 will be turned off. The voltage across the capacitor, in this case, voltage across the capacitor, VDC. Voltage across the capacitor is VDC when the load current is maximum. So if you see this one, when the initially this voltage across the capacitor is the minus VDC, so that is minus VDC. Now when the voltage across the capacity is VDC, the current is the maximum. This current is a maximum value. So this is the case. When voltage across the capacitor is VDC, then the load current is a maximum I naught value. This is the maximum value I naught maximum. So now here when this capacitor voltage is exceeds is greater than this VDC, so now the current is decreases to 0. Now here this one voltage across the capacitor is VDC means is greater than the VDC, then the load current is decreasing, that is 0, that is coming to the 0 at point A. Now SCR T1 will be turned off at point A because load current 0. So now here, so T1 is turned on here in the previous, in the already we have discussed. So now here load current is increases. So and this capacitor stores the energy in the form of electrostatic field. So and current flows in this. So now here this this current is underdamped. Underdamped case, the output current is like this. When it is comes to the 0, so that is when it is comes to the 0 and it T1 will be turned off. So this is a point A. So this is 2 VDC or VS. Now in the second mode, so now here this is VDC, so it comes to the 0 and again minus VDC, and output voltage equals to this I naught into R. This is the R. So V naught equals to this R into I naught. V naught into R. This is the output voltage. And next here in the mode 2, this T1 and T2 both are in off position. So from point A to B, the load current becomes 0, and now here T1 is off, again T2 is also already is on. T1 and T2 both are in off. So now this duration is dead time. So now here this is A and this is B. Here is a I naught maximum. So now this is a VDC and this is 2 VDC, and now here this is a V naught equals to I naught into R. This is the AB. This during this period T1 and T2 both are in off. Here T1 is only turned on. And when at B point, this is the time T1 and this is the time T2. At B point, so now here T2 SCR will trigger. So now here triggered this T2, this is T1 and T2. Already capacitor stores the energy in the form of electrostatic field. So here current is in this direction, when it is in this direction, and current flows in the reverse direction. Current flows in the reverse direction. Again, it backs to the Z maximum value. So at this point, and again decreases in reverse direction and come back to the zero. So this is the case VDC2, and it come back to the minus VDC. Same fashion, but it is in reverse position. This capacitor discharges. Here is capacitor is charging in the previous one from 0 to T1 and 0 to suppose 0 to A, as capacitor is charging. From A to B, both are in T1 and T2 are turn off, and B to C capacitor discharges. So in the reverse direction, same procedure, but it is in negative. Now here VC is minus plus VC2 minus VDC2 minus VDC. Same way here VDC2 plus VDC, and it is same as V0 equals to I0 into R. So this is the case. And next in the second cycle is also same. In this case, again T2 will be turned off at C, and here T1 and T2 both are turned off. Again next cycle repeats. So that is here in the mode 3. In the mode 3, what will happen? T1 and T2. So T1 is turned off. So here, so what will happen? T2 is turned on at point B only. At point B, T2 is turned on at point B. So now here it receives the positive voltage cavity. Previously it is minus VDC. So now here it receives the positive voltage cavity, that is 2 VDC, and it discharges through this T2 and this RL, and the load current becomes 0. Then it becomes the negative direction. So now here when it is becomes 0, it is a maximum value. And next here, so now here capacitor discharges from 2 VDC to minus VDC, 2 VDC2 and minus VDC. And next here, during this time SCR T2 will be turned off at point C. At point C, so T2 will be turned off at point C. B to C, T2 will conduct. So now here automatically turn off at point C due to the load current 0. It is also same, it is plus and minus DC excitation given to RL circuit. So now here, so the positive here, in this case T2 is turned off during C and D, and T1 is again turned on. So here D, and this is always, this cycle repeats for the next cycle. And AC output voltage first half cycle generates due to DC voltage. This point is important. Due to DC voltage, first half cycle will generate, and due to the capacitor, second negative half cycle will be generated due to the capacitor. So this first half cycle, this is because of this battery, the supply voltage and DC voltage, and because of this capacitor, this negative voltage will, this is always time delay kept between the SCR turn on and other turn on. There is a time delay process, and here DC output will be get short circuited due to continuous conduction of both SCR. So there is no time delay between SCR and S. So now here AB and CD. So this AB and CD. So this time duration, this C and this D. So this time duration is known as a dead time. Dead time or turn off, specific turn off time. So now here in this case, so here what will happen? So this is T1 time, this is T2 time, A, and this is B. This is that is the T1 will conduct, T2 will conduct, and next T3 and T4. So now here, what do you mean by inverter circuit? So here inverter circuit, so maximum frequency here. So now here this duration is known as a, this frequency. This is the total time period T, total time period T, and now here T by 2 equals to, here this duration equals to F equals to 1 by pi by, so T equals to ringing frequency omega equals to, here omega equals to ringing normal inverter frequency is omega and ringing frequency is omega r. So now here this time duration is pi by omega, and next this time duration is pi by omega r. This is the ringing frequency. So up to this point, omega by pi by omega. So now here this is the T off. This is the case. So now here what will happen first? So here the characteristics equation of this RLC circuit, S square plus R by L plus 1 by square root of LC equals to 0. That means this is the current equation. By selecting proper values of R is less than or equals to square root of under root 4L by C. So that is the condition. The system must be under damped, then current becomes 0 and SR T1 will be turned off. Same fashion for T2 is also. This is T2 T2 conduction is just because of this positive off cycle is just because of supply voltage, and next this negative off cycle is just because of the capacitor only. So now here what about the ringing frequency formula? Ringing frequency omega r equals to, so now here 1 by LC minus 1 by r by 2L whole square, that means r square by 4L square. So this is the ringing frequency formula. So now here what is the maximum frequency formula? So now here this is the T by 2 equals to this T by 2 equals to, so off cycle, for the off cycle this is the total time period. This is total time period T. So T equals to total time period T equals to T by 2 plus T by 2 plus T off plus T off. So this T off plus this T off and this T by 2. T by 2 equals to this T by 2 equals to what is the formula? So what is the formula? That equals to pi by omega r. And next here this T by 2 equals to same T by 2 plus so this what is the formula for maximum frequency here? So maximum frequency F equals to 1 by T total time period. So that equals to here T by 2 plus, so T by 2 plus, so 2 into 2 T offs. So that is 2 frequencies, 2 offs. So that is T off plus T off time period. So now here this equals to T by, so now here this is 2 pi by here, that is square root of 1 by LC minus 1 by R by 2 4 R square L square, that is plus 2 into T off. So that is the formula for maximum frequency. So now here this is the next. Here what are the limitations? Here limitations equal what are the limitations? So the load current flows during positive off cycle from the source only, from the DC supply only. So here positive off cycle, and here in this case DC supply gets short circuited, T1 and T2 again simultaneously turn on. And next the rating of commutating components, that means L and C should be high just because of load current flows through it. And the load voltage waveforms gets distorted if the dead zone time, that means dead time or SCR turns on time is high. And then maximum output frequency of inverter should be less than the ringing frequency. So now here in this case omega r, so now here omega frequency is always less than here ringing frequency. Now here this DC voltage source is short circuited if the output frequency of the inverter is higher than the ringing frequency, and the maximum current that is during each high cycle, its time duration depending upon the load, this will result poor regulation of the inverter output. These are the limitations. So now here another advantage, in order to overcome the limitations of the here this limitation. So now here this maximum frequency, output frequency, always less than the ringing frequency. So to overcome this one, so here in the modified series inverter, so we can inverter maximum frequency greater than, we can make the inverter frequency greater than the ringing frequency. Omega is greater than omega r. So that is the case here. This is the supply voltage as it is. And now here this is another case. This is one thyristor T1, and next here this is the two inductors, and next here this is the case, and next this is the thyristor T2, and now here this is the capacitor, and now here this is the resistor. So now this is the circuit diagram. Let me change the color over here. So this is the supply voltage VDC or VS, and this is the T1, this is the T2, and this is L inductor, and now here this is the C, and this is the R. So this is the modified series inverter. So in the first mode here, same fashion here. So in the first mode, what will happen? So current is flowing. So this is the plus and this is minus, and current flow is flowing through T1, this L, and next through C, and this D, and again come back to the negative. VDC plus VDC plus T1 L, and next C R, and next minus VDC. And next in the next case here, so let me change the color over here. So this is the color. Next case here, capacitor stores the energy in the form of electrostatic and it will discharges. So that is the case. So here this is the case. In the previous one, this is the direction, current direction. So now here the current is flowing like this only. So in this case, the current direction is like this. So this is the modified series inverter in this case. So the ringing frequency is always, if we can make the ringing frequency less than the inverter frequency. So now here parallel inverter. What about the parallel inverter? The parallel inverter. So what are the components in the parallel inverters? The components in the parallel inverters. So this is the one center tapped transformer we are using. This one is a center tapped transformer. So used, you can call it as a center tapped inverter. So this is the one. So now here this is the N2, this is the N1. So the so this transformer primary is connected to this DC supply and secondary is connected to the load, that is the load resistor R. And now here this number of turns in the secondary is N2 and the primary winding turns are N1. So this is the inductor and this is the capacitor and this is the T1 and this is the T2. Here we are giving the supply voltage VDC. And now here this is the middle point. So now here what are the modes here? So now that I will explain. So first here commutating components. So what is the name here? The commutating components. So that's C and L. So C and L are connected across the supply. Connected across the supply means it is also parallel inverter. So turns ratio of primary winding and secondary winding, so that must be N2 by N1, that is should be 1. So now here S1 and S2 are two main thyristors from which the load current passes through it. So here class C like commutation circuit, class C commutation, this is T1 and this is T2, L and C. So when T1 is turned on, so T2 will be turned off, and in the complementary fashion T2 is turned on and T1 will be turned off. So now here in the mode 1, what will happen in the load 1? So first current will load current flows through the path first case. So now here let me write. So here current is flowing through that inductor. So like this through L. So now here the current direction. So now the current direction, let me change the color over here. The current is from the plus and minus. So here this is the current direction. This is the case current direction in the mode 1 operation. VDC, L, and next this is a, this is A, and this one is a C, and next here T1, next thyristor T1, and next VDC, again come back to the VDC, and SCR T1 is turned on in this case. Now it will generate the flux and the resulting EMF will be. So now here the resulting EMF is here. Let me change the color over here. This is plus and minus. So here this is the plus and this is a minus. So now here in this case this is the plus and this is a minus. So now here the resulting this will generate the flux and the resulting EMF on the primary winding AC. So this is the A, this is the A, and this one is the C, and next BC. So this is C, I think. So C, and this one is the A, and this is the B. So now this is the C. So now here this voltage, and now here the charging of the capacitor is done up to 2 VDC due to this inductance. The polarity of the C is done, that is plus and minus. And now the maximum voltage withstand the capability of the SCR T2 is VDC. The now induced EMF in the transformer secondary winding is 2 VDC, and now here that is it is 2 VDC means turns ratio is 1 means here unity means here this is also 2 VDC. So now here output voltage, here current will flows, here induced EMF will be developed in the transformer secondary winding, and so here current flows in this direction. So this is the output voltage VR, and this will result current flowing through the this one. In the mode 2, what will happen? So now here in the mode 2, T2 will be turned off. So now here this is the case in the mode 2. So now here capacitor voltage 2 VDC to in the mode 1 2 VDC to VDC. It will decreases, and this is the thyristor voltage, output voltage. So capacitor voltage, this is the output voltage, and this is the VDC, and now this is the capacitor current. So now here what will happen when T2 will be turned off, T2 will be turned on. So now here T2 will be turned on means here. So let me change the color over here. So this is the case. So this is the case. So now here T2 will be turned on means here this is the case. So this is a minus and this one is a plus. In this case T1 will be turned off. So that case I will explain. So first here what will happen in the mode 2, SCR T2 is turned on, SCR T2 is turned on. So T1 will be turned off. The capacitor voltage reverses. This is the minus and this is the plus. Here current flows in this direction. So now here, so that is capacitor voltage reverses, VDC is applied across it. So this VDC is applied across it. So it will be turned off. So T2 is turned on. So the load current flows through VDC. So that is VDC. And next this L, this C, this is a C and this is a B. And again T2 and next again come back to the VDC. Capacitor is charging again, come back to the minus VDC voltage. And now here current flows during the during this interval, the reverse direction as that of when SCR is turned on. Next cycle repeats. The SCR T1 is again turned on when it receives the gate pulse and T2 will be turned off. When T1 will be turned on, so T2 will be turned off. When T2 will be turned on, T1 will be turned on. The waveform of output voltage becomes rectangular. That is, rectangular means that is the sine wave. So if you are giving the DC input, so you are getting the rectangular means that is the AC output voltage. So by switching T1 and T2. So now these are the waveforms Here output voltage, this one is the output voltage. So now here, I hope all these concepts are clear to you regarding series inverter and parallel inverters. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.